Hello everyone, and welcome to this new series of lessons which we have called Working with Vectors. By the end of this lesson, you would be able to identify the forces acting on a body when it is at rest on an inclined plane. We have chosen this title, Working with Vectors, for this new series because the situations involving vectors are those which come from various working environments. In this lesson, we will introduce the inclined plane. In our first lesson, we are going to think up the easiest way of lifting a heavy load into a bakkie. Here we have a man confronted with the problem of needing to load a crate onto the back of a bakkie. Nearby, there is a boy resting under a tree pretending to be asleep. The man walks around and around the crate, wondering how to get it onto the bakkie. He tries to lift it. It is too heavy. He looks around for help. What do you think the man should do? The man at the bakkie stops a passerby and asks him to help. The two of them struggle together and finally lift the crate onto the bakkie. You can see that it takes huge effort to lift it straight upwards onto the bakkie. A second man must be called to help do the work. And this is exactly why man invented machines, to make it easier for us to lift heavy loads. Let us go back to our man faced with the problem of lifting a heavy crate onto the back of a bakkie. There is a much better solution. Instead of lifting the load directly onto the bakkie, it would be a lot easier to push the load up onto the bakkie using a ramp or an inclined plane. A person of much less strength could in fact manage. Let us discover why. In this lesson, we are going to deal very specifically with the forces acting on a body when it is at rest on an inclined plane. Now, this whole concept of an inclined plane is as old as time itself. Well, not that old, but certainly 7,000 years old. There is a theory that the Great Pyramids of Egypt were built in this way. By creating a ramped incline with sand, they got Hebrew slaves to push these 2.5-ton blocks up the incline and place them in position. Now, how does the inclined plane work? Let us use this lesson to examine all the vector forces related to making it easier to lift an object through the height where I have drawn a red arrow. We are going to examine the forces that act on a body when it rests on an inclined plane. But I would like to begin by examining the forces that act on an object standing on the ground. Here we have an ordinary cardboard box. Ignore the fact that it contains an elephant. Let's just say it is heavy. What forces are acting on this box? Well, there is the weight acting downwards, which is the force due to gravity, and the normal force is the force acting at 90 degrees to the surface. Now look at this diagram. This line represents the weight of the body, and it pulls the box down towards the center of the earth. But the ground or the floor surface exerts an equal and upward force on the body. We call this force the normal force because it is perpendicular to the surface. Now, in this context, the word normal means is perpendicular to. The body is in equilibrium because it is at rest on the floor. Now, when something is at rest, this means that there is no resultant force on the body. Now, if we add the normal force and the weight of the body, we have the normal force plus the weight is equal to 0. We will find that there is no resultant force. Therefore, the normal force must have the same magnitude as the weight. Look at this diagram. To show that they have equal magnitudes, I will mark each of them with a little line, as we do for lines of equal length in maths. Remember that the normal force acts in the opposite direction to the weight. Now let us return to our box. Let's get a strong man to lift the elephant box so that it rests on an inclined plane. As you can see, an inclined plane is just a flat surface which has been raised so that it makes an angle with the horizontal. As we raise the flat surface on which this body rests, we have made an angle between the inclined plane and the horizontal. Let's consider a force that acts on a body as we raise the surface through a small angle. Here we have a piece of hardboard that has a rough surface and a smooth surface. We place the box on the smooth, frictionless surface. The body will slide down the slope. There is a resultant force acting on it. Here we have an inclined plane on a rough surface. It exerts a frictional force on the body and keeps it from sliding down the plane. Let us look at this in a diagram. There are three forces acting on the body when it stands still along the inclined plane. They are the weight, which always acts vertically down towards the center of the earth. Then there is the normal force on the surface on the body, and this force acts at 90 degrees to the surface. Finally, there is the frictional force which acts along the surface of the plane. This force opposes the downward motion of the body and stops it from sliding down the plane. The body is at rest on the plane, so the three forces are in equilibrium. They will form a closed triangle of vector forces because they have no resultant force. Now let's draw that triangle of vectors for this body on the inclined plane. The weight acts vertically down towards the center of the earth. It is often easier to start with the weight, perhaps because it is the simplest to deal with. Now at the head of this weight vector, we draw a horizontal line. This line represents the horizontal surface. Now you will need to use your protractor to measure the angle of inclination. For the purposes of this demonstration, I will be using any angle. We draw the surface of the plane to show in which direction it slopes. Now remember to mark in the angle of inclination. We call the angle theta. Now from the tail of this weight vector, we drop a perpendicular line down onto the inclined plane surface. Now this line represents the normal force, and as you know, it is perpendicular to the inclined surface and acts in an upward direction. Finally, we draw the frictional force which acts up the surface of the plane, and it prevents the object from sliding down it. Now we can pay some attention to the angles of one force to another. Now the angle between the normal force and the frictional force, this angle here is a right angle. And the angle between the weight and the frictional force, this angle here is 90 degrees minus theta. You can see this from the fact that the weight makes a perpendicular with the horizontal line. Now the angle between the normal and the weight, this angle here, is equal to the angle of inclination which we have called theta. This is a very useful fact to recall when you are solving problems. Notice that in this triangle of forces, the vectors are placed head to tail. This is because the forces are in equilibrium and the body is at rest. Now we want to see how changing the angle of inclination affects the size of the normal and the frictional force for a body at rest on an inclined plane. From an angle of inclination of 0, we lift the inclined plane at a steady rate. And as the angle of inclination increases in size, so the normal and frictional forces change in magnitude. I have drawn the triangle of forces at different inclinations. In these diagrams, the weight is equal to 10 newtons, and I have drawn a line of 10 centimeters acting downwards. Using the scale 1 Newton represents 1 centimeter, we find that the normal force is 9,4 newtons and the frictional force is 3,4 newtons when theta is 20 degrees. Now when theta is 40 degrees, the normal force is 7,7 newtons and the frictional force is 6,4 newtons. Here the normal force is 5 newtons and the frictional force is 8,7 newtons when theta is 60 degrees. Which of these inclined planes will make it easiest to lift the heavy load onto the truck? The 20 degree, the 40 degree or the 60 degree plane? Logically, you can figure out that it would be easier to push the weight up this surface than it would be to push the weight up this surface, because you would be pushing against gravity and the weight would want to slide down due to gravity. Let's explain this in scientific terms and look at two of these vector diagrams. Can you see that when the angle is smaller, the normal force is bigger and the force parallel to the slope is smaller? Now at an angle of 20 degrees, we have the normal force that is 9,4 newtons. In comparison, when the angle increases to 60 degrees, we have the normal force at 5 newtons and the force parallel to the slope increases and it's 8,7 newtons. This means if I want to push a box up a slope where the angle is small, for example 20 degrees, I will need a smaller force. Now it's time for today's task. A box with a weight of 500 newtons is placed on a plane inclined at 20 degrees. The box remains stationary. Construct an accurate scale diagram to find the magnitude of the normal force and the frictional force on the box. We have come to the end of today's lesson. In it, we have examined the inclined plane as a useful machine. We have also examined the forces acting on a stationary body that rests on the plane. Oh, by the way, let's see what was in our box saying elephants in transit. So, there was an elephant in the box. And look how beautiful it is too, made by our fantastic craftswomen who are unique to South Africa. Well, that's all from me. Until next time, goodbye.